Hi, I'm Caesar. Welcome to this Real Python video course on the Math module. What is the Math module? The Math module provides access to some of the mathematical functions defined by the C standard library, and much more. The module contains functions that perform computations from number theory, combinatorics, trigonometry, geometry, and classification. Many Math module functions are thin wrappers around C Math library functions. Let me show you one. If you go to the GitHub repository for Python, go over to the CPython directory, you'll find the mathmodule.c function. In that file, you'll see this definition for the mlog function, which implements the logarithm function that we'll talk about in this course. If you take a look at this code, you see that this is a very thin wrapper around the logarithm function in the C standard library. But the math module functions do more than just this. There are some nice functions that were added in Python 3.8, and we'll discuss these. So why use the math module? Well, for one thing, it's part of the standard library of Python, so there's no need for a separate installation. All you do is import the module with import math. The math module functions have been tested and optimized to give accurate results. So there's no need to reinvent the wheel to perform basic math. Just load the module and get going. Here are the topics that we'll discuss in the course. We'll go over some of the constants in the math module. Then we'll talk about arithmetic functions and then power functions, the exponential functions, logarithmic functions, and other functions in the math module. And then we'll take a look at some of the new additions in Python 3.8. Then we'll discuss the differences between the CMath module, which deals with complex numbers, and the math module, and NumPy and the math module. We'll wrap things up with a summary. Now, I'm eager to get going, and I bet you are too, but one last important thing before we do. All of the code in this course was tested in Python 3.9. You should be fine with Python 3.8, and probably even as low as 3.5. But if you do want to test the new functions that were added in Python 3.8, you may want to have at least that version of Python installed. All right, enough with the particulars. Let's get going with this course. We'll start by taking a look at the constants defined in the math module. The math module defines 5 constants. Perhaps the most famous constant in mathematics is pi. The symbol that's given to the numerical value of pi is the Greek letter p. The value of pi is around 3.141592. It's an irrational number, and so the number of digits continue on forever with no predictable pattern. The value of pi is a sort of universal constant in the sense that if you take any circle and you take its circumference and divide it by the diameter, you're always going to get the value of pi. Now, in Python 3.6, the constant tau was introduced, and this is the value of 2 times pi. Perhaps the next most famous constant in mathematics is Euler's number. This is usually given the letter E, and E is around 2.718281, and this is also an irrational number, so the number of decimal digits continues on forever with no predictable pattern. E comes up a lot when you're working with problems that involve exponential growth and decay, and it comes up also a lot in calculus and in compound interest, and we'll take a look at an example involving decay in a future lesson. And then there are other 2 constants in the math module that are not technically numerical values, but more of a conceptual values. The first one is the infinity constant, which is denoted by inf. The inf constant is there to encapsulate the mathematical concept of something that's boundless or never-ending. Sometimes in an algorithm, what you want to do is compare a given value to some sort of absolute maximum or minimum, and this is where the inf comes in. The other conceptual type of constant is nan, and nan is there to represent the idea of not a number. This comes up sometimes when you're doing a numerical computation and maybe your data gets corrupted in some way, or you do an invalid mathematical computation, like say dividing by 0, then a lot of programming languages will return a value of nan, or not a number. All right, let's take a look at these constants. First things first, go ahead and import the math module. Let's take a look at the pi constant, and we've also got Euler's number, and we've got tau, inf, and nan. Let's work through an example showing why you would want to use the constants in the math module. We'll do this for pi, but similar ideas will apply to the other constants. Let's suppose you have a sheet of material that has a radius of 5 feet. Then you know, back from grade school, that the area of the sheet would then be pi times the radius squared. So the area is around 78.53. Let's suppose instead that you computed the area, say just using 3.14. So the area using 3.14, about 78.5, which is just this value rounded to the first decimal place. Now, let's suppose that you needed to buy a lot of these sheets, and the price that you need to pay per square foot of the sheet is, say, $39.49. So let's define the cost per square foot of the sheet, $39.49. So if you compute the cost of the sheet using the cost per square feet times the area of the sheet obtained by computing the area using the built-in pi constant from the math module, and if you compute the cost using, again, the cost per square feet, but at this time using the area computed by using just 3.14, the difference now is $1.57. Not a huge difference, but already we see that there's a non-trivial difference when using an approximation to pi of 3.14 instead of using the value that comes in with the math module. Now, things will get worse if, for example, you have a lot of sheets to buy. If you needed to buy 10,000 of these sheets, then the cost that you're underestimating in what you'd have to pay to buy all 10,000 sheets is $15,723. So this is just a quick example of why you would want to use the built-in constant pi in the math module if you were going to do any type of computations involving pi. Let's now take a look at inf. I'll let you explore nan on your own time. So inf, again, is INF. The inf constant in the math module was introduced as an equivalent to the float inf value. So in the float constructor, if you pass in a value of inf, the string inf, this is going to be equivalent to the math inf constant. Whether you're using the float inf value or the math inf value provided in the math module, they both represent the concept of infinity. So for example, if you compare the math inf value with, say, the maximum size of a floating point number, which is 1 times 10 to the power of 308, you're going to get true. If you multiply the math inf value by -1, then you're going to get the concept of negative infinity, and this is less than the largest negative float value that you can store. And so in this case, again, you're going to get true. Now, to make it clear that this math inf constant is not really a numerical value, but more like a concept, if you add to math inf a value, say, of 1, and you ask whether that is greater than math inf itself, you're going to get false. So again, the idea there is that math inf is not there to really represent a numerical value, but more like a concept of boundedness or without end. Those are the constants that are contained in the math module. Coming up next, we're going to take a look at some of the built-in arithmetic functions that are in the math module. In this lesson, we'll begin our exploration of the arithmetic functions in the math module. In particular, we'll take a look at an example involving the factorial function. The math module defines many number theoretic type functions and a few classification type functions. So there are a few functions that have to do with rounding and these are ceil, floor, and truncation or trunk. And then there are a few for combinatorial computations. These are factorial, perm, and comb. And then there are some classification type functions. So these all return a Boolean. And then there are functions that are reducers. So these are functions that take either an iterable as an argument or a variable number of arguments and then produce a single value. So definitely take a look at the online documentation for the math module so you can see what all the other functions are and some examples. Now, I wanted to show you an example as to why you would want to use some of the functions in the math module instead of, say, building your own functions. And I wanted to do this using the factorial function. So you may remember from, say, high school math that n factorial, where n is a positive integer, is the product of the first integers from 1 through n. Now, here n is supposed to be a positive integer. However, for convenience, we define 0 factorial to equal 1. So here are some examples of computing a factorial. So 3 factorial, 1 times 2 times 3, that's 6. And here's 6 factorial. And notice that these are nested. There's factorials within factorials. So 6 factorial contains 3 factorial, 1 times 2 times 3. It also contains 4 factorial, and it also contains 5 factorial. So a way to think about computing 6 factorial is to compute 5 factorial and then multiply it times 6. And we'll take advantage of this when we write our own implementation using recursion of the factorial function so that we can compare it with the factorial function in the math module. All right, let's take a look at this. Now go ahead and try some computations with the factorial function. Go ahead and compute, say, the factorial of 6. You saw that this should be 720. Now, you also saw that factorials are nested. So the factorial of 6 can be computed by first computing the factorial of 5 and then multiplying that by 6. Let's compare the implementation of the factorial function with, say, some natural ways that you would write your own version of the factorial function. Computing n factorial involves multiplying the integers from 1 through n. And so maybe a way that you're already thinking about writing a factorial function is to use a for loop. So here's an example of using a for loop to implement a factorial function. The code for this function is provided underneath the description of the lesson. You first want to do some error checking just to make sure the number entered is positive and it's an integer. And then if it's 0, you want to return 1. And then initialize a output variable to 1, run a for loop that multiplies the factorial times k, and then you want to return factorial. So go ahead and run that. And then here's a version using recursion. We do the same error checking. We return 1 if the input is 0. And then you saw that if you want to compute the factorial of num, you can compute it by first computing the factorial of num minus 1 and then multiplying by num. So here we're using recursion. We are calling the same function within the function. And so that's the main idea of recursion. So go ahead and run that. And so what we want to do is we want to compare those two functions with the built-in factorial function in the math module. Now let's quickly make sure that we wrote those functions correctly. Okay, so you get the same answer with one test case. You declare that these functions are ready to be shipped. And so now let's just test them for computational speed. To compare the functions, we're going to use the timeIt module. So go ahead and import timeIt. And timeIt has a function called timeIt. Let's take a look at the help documentation for that so we quickly find out how to use this. The timeIt function is going to take in a statement. That's the code that we want to execute. And the number of times that this code will execute is 1,000,000 times. That's the default value. We can change that by passing it a value to the keyword argument number. Now, before we execute this function, we may want to run some setup code, maybe importing a module or something. And then the other thing to take note is that if we have some variables defined in this code here, and those variables, for example, are stored in the global namespace, then we want to pass in the global namespace to this keyword argument globals. Let's do this real quick so you can see what I mean. Let's use the time it function for each of the 3 different ways to compute the factorial function that we have right now. Create a variable called with loop, and let me bring up some code. Here, we're going to execute the fact loop function evaluated at the integer 10, and we need to bring in the global namespace because we define fact loop in the global namespace. And so go ahead and run that. And then you want to do the same thing with the recursion function. All right, that seemed to take considerably longer. Now let's go ahead and do the same thing, but with the built-in factorial function. So we'll create a variable called with factorial. And here we need to have a setup value, and the setup value is going to be import math. Okay, so run that, and that seemed real fast. Now let's take a look at the 3 values. So with a loop, and then with recursion, and then with factorial. With the factorial, it's about 10 times faster than the loop and significantly faster than with recursion. The main reason why the factorial function from the math module has a much shorter execution time, and it's going to be generally the case for a lot of the functions in the math module, is that these functions, they are thin wrappers around the corresponding math functions in the C standard library. And those functions in the C standard library, they've been around for a long time. They're highly optimized. And so we reap the benefits of that in Python if we use the math module. All right, coming up next, we'll take a look at functions in the math module that round floats to integers. Rounding floats to ints. Let's see the functions in the math module that do this. There are 3 functions in the math module that round a float to the nearest integer. The first one we'll take a look at is ceil, which is short for ceiling, and ceil of x returns the nearest integer greater than or equal to x. So if you think of the real numbers as points on a number line, when you take the ceil of x, this will round to the right. And so ceil of x will return the integer that's closest to the x, but on the right of x. Next is the floor function. Floor of x returns the nearest integer less than or equal to x. So on the number line, floor of x is going to be the integer that is to the left of x and closest to x. Now, this can get a little tricky when you are dealing with negative numbers, and we'll take a look at some examples. But if you keep the analogy of the real numbers as being points on the number line, floor of x rounds to the left on that number line. And then lastly, we've got trunc, which is short for truncation, and trunc of x returns the integer part of x. So if x is a float and it's got digits after the decimal point, we drop all those decimal points and keep the integer part. If we think of x as being a point on the number line, we are rounding towards 0. The rounding function trunc is a composition of floor and ceil. Let me show you what I mean. Because trunc rounds towards 0, we can write trunc of x in terms of floor and ceiling, depending on whether x is greater or equal to 0 or whether it's negative. So if x is a positive number, a positive float, then trunc of x will be rounding to the left, and so that's equal to floor of x. But if x is negative, if we want to round towards 0, what we want to do is round to the right, and that's what ceiling of x does. So to clarify everything, let's just look at some examples. Let's start off with ceil. Round to the right the number 5.43. Another way to think about it is that we're rounding up. But again, think of the numbers as being the numbers on the number line. Rounding to the right with ceil gives us the integer 6. If instead we use a negative number, so negative 12.3, here we're rounding with ceil, so we're rounding to the right, and the nearest integer to the right of negative 12.3 is negative 12. Now let's use the floor function with these same numbers. 5.43, floor rounds to the left, so we get 5. And if we round negative 12.3 with floor, rounding to the left gives us negative 13. Now let's use trunc, the truncation of 5.43. This will get rid of the decimal numbers 43, and so we get 5. And if we do this with the negative number, negative 12.3, we're getting rid of the 0.3, and you get negative 12. Let's confirm the formula that you saw for the truncation function. When the input value is a positive number, that is going to equal the floor of the number. And when the input value is negative, the truncation of that number is going to equal the ceiling of the number. So those are the functions in the math module that take an input number and round to the nearest integer. In the next lesson, we'll take a look at a function in the math module to help you decide when two floats are close. How close depends on your relative tolerance.